whoever you are. Are you confused with an upside down delta? A delta looks like a triangle with a dot over cross next to it. This is called the colon divergence. To tell you which one is which, an upside down triangle with a dot next to it is the divergence of a vector field, and an upside down delta with a cross next to it is the curl of a vector field. Okay, to start with, a vector field is a field of vectors as shown. Some examples are like this.
Okay.
And then or this. If I were to put a velocity in a vector field, it would the velocity would go some in the direction that it was pointing. Like the most common example of a vector field is fluid flow. So like if you have a pond like this one, and if you were going to throw a stick in that pond, where would it go? Easy. The arrows are all pointing to a point, so the trick goes to that point. But what about the divergence? The divergence is negative. How do I know this? The divergence is how much a point is acting like a sport. If the point acts like a sink, its divergence is negative, and if it acts like a sport, its divergence is positive. Oh wait, you know that the divergence is negative, but exactly how negative? Don't know. Now without the vector function, let's say the vector function is x squared plus the x component, or a, is x squared plus y to the power of 4 minus cosine of x cubed plus y squared. And then the b, or the y component of the function, the vector function, is y to the power of 4 plus x cubed plus sine of y squared plus x to the power of 4. To find the divergence, you need to do this. The divergence of a is equal to partial a, or a is the x component, over partial x plus partial b, or the y component, over partial y. And that is equivalent to, in this case, 2x minus sine of 3x squared plus 4y3 plus cosine of 2y. What? You're probably confused. I bet it's the partial derivatives that you're worried about. Do you know derivatives? You should read my paper on it. Okay, take the term partial a over partial x. Here's a trick. Oh, never mind. No, sorry. Oh, by the way, x squared plus y to the power of 4 minus cosine of x cubed plus y squared, and y to the power of 4 plus x cubed plus sine of y squared plus x to the power of 4 is equal to a over b. And partial a of partial x only cares about the derivative of x. Y is 0. So plug in y equals 0 and x equals first derivative of x. Therefore, since the derivative of cosine equals sine, it's 2x plus 0 minus sine of 3x squared plus 0 is equivalent to 2x minus sine of 3x squared. Get it? Okay. Let's see the divergence of the point in a vector field that goes with a graph. Say the point 2, 3. Remember, this is likely not going to be negative because the vector function doesn't go with vector pond. So 2 equals x and 3 equals y. Let's plug it in. 2x minus sine of 3x squared equals 2 times 2 minus sine of 3 times 2 squared that's equivalent to 4 minus the sine of 12, and that's equivalent, well, approximately equivalent to 4.5. Cool. But hold up, we're not finished yet. But so we need to find partial b over partial y. This only cares about the derivative of y, not x. x is 0. And this time we're only looking for the derivative of b with respect to y. So instead of doing x squared plus y power of 4 minus cosine of x cubed plus y squared, we're looking at b. Y to the power of 4 plus x cubed plus sine of y squared plus x to the power of 4. And this time, the partial derivative will only end up with y's. Okay, remember, x equals 2 and y equals 3. Ready, set, compute. Oh, and by the way, partial b over partial y is equal to 4y3 plus cosine of 2y. 4y3 plus cosine of 2y is equal to 4, and well, in this case, equal to 4 times 3 cubed plus cosine of 2 times 3 is equal to 108 plus cosine of 12, and that's approximately equal to 109. Now you add them up. 109 plus 4.5 is 113.5. So the versions at the point 2, 3 on the vector field that goes with the vector function. X squared plus y to the power of 4 minus cosine of x cubed plus y squared, and then y4 plus x cubed plus sine of y squared plus x to the power of 4 is 113.5. But where does the core come in? Wait. Now, instead of using the upside down triangle dot, looks like that. Anyway, representing it, it's upside down triangle cross representing it. What is core? A core is how much magnitude is pointing in clockwise directions. If something is pointing in counterclockwise directions, it has negative core, and if it's just pointing straight, its core is 0. So if you take another pond, and it looks like this, and let's throw a stick in, what will happen to the stick? It will rotate in a counterclockwise direction. This means that the lake has negative core. The mathematical formula is core of A is equal to partial A over partial X minus partial B over partial Y. Now let's find the core of the same vector field. Let's do it at point 3, 2. 2x minus sine of 3x squared is equal to 6 minus sine of 81 is approximately equal to 6.6. Now let's find the partial b over partial y. 4y cubed plus cosine of 2y is equal to 512 plus cosine of 4, and that's approximately equal to 511.3. Now you subtract. 6.6 minus 511.3 equals negative 504.7. So the core at that point is negative 504.7. Okay, so we know what core of the upside down triangle times and divergence upside down triangle dot is, but why? What was the point of all this? These equations that I'm about to show you are legendary. About electromagnetism, I present to you Maxwell's equations. The divergence of D is equal to phi over epsilon 0. Divergence of B is equal to 0. Curl of E is equal to negative partial B over partial T, and the curl of H is equal to partial D over partial T plus J. Let's go step by step. Let's see the first equation. Example. The divergence of D is equal to phi over EO. This actually means the divergence of D is equal to phi over EO epsilon 0, then that's equal to total charge over total volume. And say you have an electric field E, this is supposed to be D, and you wanted to find the divergence by an electron with a 5-column charge. You could use the method divergence that I taught you, or in this case, that's divergence of E that's supposed to be D, I'm sorry. And that's equal to partial A over partial X plus partial B over partial Y. Or you could use divergence of D is equal to pho over epsilon O. Both work. But now let's do pho over epsilon O. Anyway, the electron, like all electrons, has a volume of 10 to the negative 3 m cubed. Therefore, the divergence is 5 columns over 10 to the negative 3 m3 cubed. But anyway, here's what it's stating. There cannot be a zero divergence in an electric field if there are any protons or electrons. So that means this can't be possible, that vector field. Do you know why? It's because it has to have a positive divergence, because there's a positively charged particle in there. So anyway, here's the equation in the words. The divergence of an electric field is equivalent to the electric charge density. What about the second Maxwell equation? The divergence of B is equal to 0. It was my first thought when I saw this equation. Why isn't the divergence of B equal to magnetic flux density? That was because B equals magnetic flux density. And look at this. If the divergence of D, electric flux density, is the electric charge density, why isn't the divergence of magnetic flux density equal to the magnetic charge density? It is. It's just that it's always 0. Think about it. You have a magnet, looks like that, dipole. And you break it in half. Looks like that then. See, no matter how many times you break it, the magnet, it just creates more dipoles. And basically, no one has ever found a magnetic monopole. Therefore, the divergence of B is equal to 0. I think that covers up the second Maxwell's equation. What about the third? The curl of E is equal to negative partial B over partial T. In this equation, the best way to think about partial derivatives is the rate of change, not the way I taught you. I honestly don't know what the unit for magnetic flux density is, so I'm going to use this. What's it called? Lowercase omega. This is easy. Let's say the magnetic flux density is 2 omega slash per second. Therefore, the curl of E is equal to negative 2 omega per second. Get it? And if the divergence were 1 omega per second, the curl of E is equal to negative 1 omega slash S. Anyway, I find this equation the easiest to understand. In the last, final, and fourth Maxwell equation, the curl of H is equal to partial D over partial T plus J. So H equals the magnetic field, and then partial D over partial T is the rate of change of electric flux density with respect to time in seconds, and J equals current density, or total current over total area. So if we have the change of D equals 2 delta per second, and J equals 14 amps over m squared, what is the curl of H? First, let's substitute. The curl of H is equal to 2 delta plus 14, and that's equal to 2 plus 14, and then that's equal to 16. So delta times H equals 16. The exclamation mark. And that's equal to 0.099922227. It's 13. Just kidding. It's 16. Okay, what's flux? You know how it said D equals electric flux density and B equals magnetic flux density? What do I mean by that? So in flux in general is how much of something in a given unit of time goes into a certain point. So if you have a hollow cylinder and you put a net on something there, how much air is going to go into that net in a given unit of time? Now let's call that net X. Now let's plug in a different net zero. We'll call it y. And as we go down, as you observe, the magnitude of the airflow decreases. So if I were to do a line graph of this, it would look like this. Magnitude time. Therefore, if net y was below net x, it would have less flux than x. If I was to place it above net x, it would have more flux. And magnetic flux, on the other hand, is how many magnetic lines from a dipole is going through its surface. Let's grab net x and net y from the hollow cylinder. Now let's put them near a dipole. Wow, those are small nets. Which has more magnetic flux, net x or net y? Well, one thing I know about dipoles is that the magnetism varies depending on how far you are. Here's a line graph. Magnetism distance from the dipole. Ugh, so many down graphs. But from the illustration in the line graph, we know that net x has less magnetism than y, and therefore less magnetic flux. And from that information, you can probably understand that electric flux is how much electricity goes through a circuit as a given unit of time.
Thanks, Louis.